Flight controls. Primary flight controls, of course, if you've flown an airplane very long, you already know, are the elevator, which controls pitch, the rudder, which controls yaw, and the ailerons, which control bank. Secondary flight controls do other things, or they might even help with those primary flight controls. Trailing edge flaps. They're there to produce a lot of lift. Unfortunately, they generally produce a lot of drag. There's several kinds. A plain flap you don't see much anymore. It just pivots at one spot and effectively changes the angle of attack, or the camber rather, changes the camber of the wing. Split flap creates lots and lots of drag. The rest of the wing is still there, and the back part of the flap goes down. So it definitely changes the camber of the wing, but drag is huge on a split flap. Fowler flap moves aft, and it comes back out of the rest of the wing, so it also increases the area of the wing. And that's generally what you would call a flap is on a 172. A slotted flap is where a part of the flap comes down. Of course, a Fowler flap also increases camber as well. A slotted flap comes down, so we get an increase in camber, and some have an increase in area. But the main characteristic of a slotted flap is that there's a place for air to go through the rest of the wing and the flap, so it maintains airflow over the flap even at high angles of attack. Generally speaking, a lot of Fowler flaps also end up being slotted flaps, and a lot of slotted flaps end up also being Fowler flaps. So let's see, I got a couple of pictures here. Here is a type of split flap, and the rest of the wing is still here, and the back portion has just gone down. Lots and lots of drag along with the lift. Here is a Fowler flap. You can see the flap position used to be in with the wing, and now it's moved, so we've added all of this area to the wing, and it looks like this one is slightly slotted. I can see air through there. It looks so. This looks like a slotted Fowler flap. And then if we look at transport category jets, multiple slots. Multiple slotted flap. And of course these are also Fowler flaps, so they're slotted Fowler. In fact, they increase the area quite a bit. And you'll notice there's actually two slots in here, so we've actually got at least two pieces of flap to increase our lift. Of course, we also get a lot of drag. Leading edge flaps. Here's type of Kruger flap. A Kruger flap, if you look at it from the leading edge of the wing, the Kruger flap just folds out, and it adds to the camber. Let's see. The camber goes up, is its biggest characteristic, and it does add a little bit of area. Of course, you're only going to fly this if the airplane is at a high angle of attack, so the wing's going to be at a high angle of attack, so the Kruger flap isn't going to look quite so strange in screwing up the airflow, or the airflow rather. And this is very common on a lot of transport category jets. I've never seen one on a little airplane. Slats are, let's see, I'll draw a picture here. So if we have a leading edge of a wing, slats actually, let's try it again. Yeah, slats actually move forward. In this case, you can see that they've been pushed forward so far. There's actually some air going through there, and sure enough, if we move that slat far enough forward, there's going to be airflow. So of course, if the airplane is at a high angle of attack, and we've moved this slat way out in front, we can get some air across the top, and we can also get the air through the slat. And this key, it maintains our boundary layer, maintains our laminar flow over the wing at high angles of attack. So when we're at a high angle of attack, we get to keep airflow over the wing, over the top of the wing. So now we can stay at that high angle of attack. Slats move. They're retracted during most of the flight, and they're extended. Typically, on transport category jets, they come out automatically when you put in enough trailing edge flaps. Slots, on the other hand, are there all the time. On this small aircraft, here's what looks like the leading edge of the wing, and out in front of it is a slot. And this, effectively, this air allows airflow between the slot, or through the slot, and the rest of the wing all the time. Of course, it doesn't move. It probably increases drag a little bit at high forward speeds, but at low forward speeds, again, we've got that slot on the front of our wing at high angles of attack. It'll really help us maintain airflow across the top of the wing, and of course, we need that airflow across the top of the wing to generate lift. Of course, trim tabs, you've seen them before. We're used to them on the elevators, but the bigger the aircraft, the more likely you're going to see trim tabs on the ailerons and trim tabs on the rudder. Spoilers and speed brakes. Spoilers, you're generally going to find, spoilers are going to be on the wings, and they're there to do two things. One, they reduce lift, and two, they increase drag. They do both simultaneously. They kill the lift and they increase drag. Here's a 737, and you can see the spoilers outboard and inboard. Here's some outboards, here's some inboards. Well, there's three sets. You just can't see that third set down behind the fuselage. So it reduces lift, which is great because now you get better traction on the wheels, and of course it causes drag, which helps slow the airplane down. So if you look at transport category jets, they pretty much all have spoilers. Now, speed brakes are typically not on the wings. In fact, we're going to say that speed brakes are not on the wings, and speed brakes only do one thing, and that is to increase drag. You'll notice here on this Sukhoi, I don't know, is it an SU-27, SU-29, I don't know. Here's the speed brake, and it pops up and it increases drag quite a bit, but it's not on the wings, so it's not directly affecting lift. Here is a BAE 146, which is a transport category jet, and quite frankly, I don't know if it has spoilers, but it certainly has a speed brake. The aft section of the fuselage pops open underneath the rudder and causes a lot of drag. So this is definitely going to be a spoiler. And here on the space shuttle, the rudder pops out, and you can't see the other side. The rudder splits in half and pops out on both sides and just causes drag. So it's going to fit the definition of a speed brake in that it only increases drag. It does not reduce lift. Okay, what do these components do? Well, okay, let's talk about cables and pulleys. Cables and pulleys. Cables are made out of stainless steel. And it's a whole bunch of wires. I'll show you a picture here shortly. The pulley is this round gizmo with a little groove in it, so the cable will stay in it. And cables and pulleys are to transfer force from the flight controls in the cockpit to the flight controls out on the flying surfaces. Here is a cross section of a stainless steel cable, lots and lots of wires wound up together. Here's another picture. It's very common for guards to be put on the pulleys so this cable can't accidentally pop out, because we would hate if a pulley popped out while we were flying around. Bell cranks are there to change the direction of movement. Whoops. So let's say we got this push-pull rod, and it's moving fore and aft, and this bell crank, it's hinged right here. Now, this piece right here can go out to that flight control and go out to that flight control. And so you notice that there is a 90-degree angle change in movement. So that's what bell cranks are for. Here's another bell crank. This one's operated by cable. Here comes in a cable here. Here comes in a cable here. It pivots. Looks like it's pivoting right there. And as we pull back and forth on this cable, this push-pull rod right here is going to lift up or push down on this, looks like an aileron or a flap. Again, we're changing the direction of motion here by 90 degrees. Torque tubes. Torsion. Torque tubes. Here we go. Here's a torque tube for flaps. Somewhere inside of here is an electric motor, and here's the torque tube, and it's pushing down on the flaps, pushing down on the flaps, pushing down on the flap. So we're actually twisting. There's actually a twisting moment on a torque tube. Push-pull rods allow us to have compression and tension. That is, we can push here and it'll travel, this force will travel in a perfectly straight line and it'll push here, or we can pull on this side, pulling would be the tension, and it'll pull on this side. So we can run a force from the flight control in the cockpit out to the flight control on our wing surfaces. Here's the end of a push-pull tube, and it's hooked onto this horn, which you can't see very well, but it's hooked on to the flight control. It's probably an elevator. Here's diagrams, got some push-pull tubes and stuff. So here's a control stick. We wrap our fingers around it, and we can go left and right with the aileron, and this tube right here is getting twisted. So it's a torque tube, and it's hooked onto this piece of metal right here, and now we have a push-pull rod that goes out to the aileron. There doesn't show it, but there's probably one going out there to the other aileron. We can push this stick, pull it back and forth, and here is a push-pull rod. It can go left, forward, and back. So there's a push-pull rod hooked onto these piece of metal, and this tube going out here to the bell crank. It's in torsion, so it's a torque tube. And then here's a bell crank. Wow. So that's probably going to go out to the elevator. No, you don't have to draw that on the test. Jack screws. Here's the simple description of a jack screw. Here's a car jack. If we spin this around, this part right here, since there's threads inside, it's going to move forward and it's going to move aft. Of course, in this case, the jack's going to go up and down. But this is a jack screw. Wow, this is a jack. And it has a screw. Wow, hence the term jack screw. Now, a common place to see jack screws are on big aircraft, large aircraft flaps. Here's a flap, and it's hard to see, but here's a jack screw right here, and there's one in here, and there's one in here, and one in there. So we got a motor in here spinning this screw around, and as it rotates, it slowly pushes the flaps out, or we can rotate it in the opposite direction and pushes the flaps in. A Cessna 172 has a jack screw for the flap jack screw. Of course, it just has one inside of the wing, and it pushes on just one flap, and they're interconnected. I've just put this in for fun just because it's really cool to think about what's on the back side of the instrument panel on light airplanes. Here's a shaft that goes out to the control wheel. This is looking aft. This is looking aft with the essentially the windshield off and the top of the instrument panel off. And you can see all this junk coming up to the instrument panel. And here's what's on back. So if this gets rotated, this chain comes in. This chain comes in. And here's a pulley and cable for the ailerons. And when you pull the control wheel or push the control wheel, this whole assembly right here moves forward and aft, and it's connected to a tube that goes straight down, and way down there at the bottom, which we can't see in this picture, it's hooked up to cables that go all the way to the back of the airplane. So think about this mess next time you go flying. Large aircraft control systems typically are not just going to be powered, not manually powered. You're essentially going to have two kinds. You're either going to have boosted flight controls, just like boosted brakes, where the hydraulic system helps you operate the flight controls, and if the hydraulic system fails, it's still going to work. So let's try boosted. Let's just say we got the control wheel here in the cockpit, and we're going to hook it to a selector valve. And those cables also go to, and we'll just say that here is a flight control. Those cables also go to the flight control. So when we move the control wheel left and right, we'll say it's an aileron, it's going to move the selector valve and let go fluid to one side. The rest of it, of course, will go back to the reservoir. And it's going to help push on the flap, but so is the cable or push-pull rod that's still connected to the control wheel. So if we lost hydraulic power, yeah, we'd move the selector valve, it wouldn't do any good, but we'd still be able to move the flight control. Still being able to move the flight control when the powered system fails, that's manual reversion. That is, we can revert to manual power, and if we have boosted controls, we're always going to be able to do that. Fly-by-wire control, it typically isn't that way. If you have the control wheel is going to, sensors or commands are going to go into the computer, and the computer is going to send signal to a servo, which is really an electric rotor. Wow, maybe even we could call it a solenoid. And it is going to move the selector valve, and then when the selector valve rotates, fluid's going to go to the actuator and move the flight control. Downside is with a fly-by-wire, because there's two downsides. One is if we have electrical failure, the computer and the solenoid won't work. But if we have hydraulic failure, even if the electrical system, the computer, and the solenoid work, it'll rotate this selector valve. But if there's no hydraulic pressure, then the actuator won't get any fluid, and our flight control won't move. So generally speaking, fly-by-wire systems do not have no manual reversion. So you need multiple hydraulic systems and multiple electronic systems just in case something quits. Of course, trim, we already know about trim. We're used to in a 172 or a Seminole doing it manually, but you could have an electric motor spinning it, and I've also seen hydraulic power moving those adjustable trim tabs. Speaking of trim tabs, there's a lot of kind of trim tabs. Now, a fixed tab, you probably don't notice it very much. Here on a 172, let me change this in color here. Here on a 172, here is the fixed tab. It's fixed in that it doesn't move. You don't move it, a mechanic moves it. It's bent to trim the aircraft so it'll fly straight. So it's fixed. That means fixed means it doesn't move. And there are some airplanes that you can put these on ailerons and on rudder and on elevators, but little airplanes usually it's just the rudder, because you don't need one on the elevator because you can adjust it. Now, an adjustable tab, this is what we're used to calling the trim tab on a Cessna 172 or a Piper Seminole for the elevator. Adjustable means that the pilot can move it. So, whoops. You spin something in the cockpit, and here there's a jack screw, and let's say that you move the adjustable tab up. What that's going to do is the wind, the slipstream is going to hit it. It's going to move the elevator down. Here's the tab. And so now that's going to reduce the lift on the tail. The tail's going to go up, and the nose is going to pitch down. So you're actually moving the adjustable trim tab to move the elevator or the flight control into the position that you want. So now the airflow is going to come over here and hit that adjustable trim tab and keep the main elevator in the down position. So if somebody moves a trim tab and or the adjustable trim tab, it looks kind of like, well, it's going in the wrong direction. Well, it's not going in the wrong direction. It's going into the slipstream to get hit to push the elevator in the direction that you want it to go. That is an adjustable trim tab. And of course, we're used to adjustable trim tabs on the elevators, but there are airplanes that have them on the rudder and have them on the elevator. The bigger the airplane, the more likely you're going to have them. And here it is on a 172. We wouldn't call that an elevator. We'd call this the adjustable trim tab. Balance tab. Balance tab is there essentially to balance the forces for you. For instance, if you start moving the elevator, let's say you want to move the elevator to the down position, the balance tab it's hooked on to right here. So as this goes down, the balance tab is going to go up, effectively helping you. Since the slipstream is going to come help, it's going to help push the elevator in the same direction that you're going. You don't have any control over this. It's got a jack screw in here because this can also be used as an adjustable. But this one is set up so that the balance tab, whoops, can't spell tab. The balance tab actually helps you move the flight control. If you move the elevator back to neutral, then the balance tab would be back to neutral. So it only helps you when you're trying to move the flight control. A servo tab is kind of interesting. You're only going to find this on older, big aircraft. And that's where, when you move the flight control in the aircraft, when you move that control wheel, you're actually moving the servo tab only. Servo tab. You're only moving the servo tab. For instance, if you wanted to move the elevator into the down position and you push the control wheel forward, it would actually move the servo tab up. The slipstream would hit it, and in this case it shows an aileron, but it doesn't matter if it's an elevator. The elevator would move down, and of course the tail would go up and the nose would go down. So if you're using a servo tab, that's actually what you're using when you move the flight control to get the when you're moving the flight control in the aircraft. A servo tab is actually the part that gets moved, and then that is the only thing that pushes the flight control in the direction that you want it to go. Anti-servo tab does the exact same thing. Anti-servo tab is going to hinder. The anti-servo tab is actually going to move in the direction to try to keep you from moving their flight control too far. You're typically going to find this on stabilators, just like we have on the PA-44 Piper Seminole. When we move the stabilator, that's the whole elevator, and it's essentially acting as the stabilizer and the elevator, hence the stable for stabilizer and later for elevator. Whoops. That's my second hint, I think. There we go. If we move the yoke, if we pull the yoke back, and so that's going to make the stabilator move up. The anti-servo tab is going to move farther in the same direction, which of course now the slipstream hitting it is going to tend to try to push it back to neutral. So effectively, an anti-servo tab increases the cockpit control forces needed so that you don't accidentally over-control, so that you don't over-control. And of course, here's the picture. You can see as the stabilizer is going this direction, the anti-servo tab is moving up to try to push the whole thing back down towards neutral. Special wings and wingtips. Tip tanks. I love tip tanks. Of course, they're primarily put there to hold fuel, but of course, if you had a wing with a tip tank on it, it acts kind of like a winglet. This higher pressure air can't easily get to the top, And of course, it's going to reduce wingtip vortices. I love saying wingtip vortices. And of course, twin engine Cessnas all have tip tanks. Drooped wingtips essentially do the same thing. If you've got the wing coming out and it droops down, then it's going to be harder for the air to get, that high pressure air on the bottom, to get to the top. And so we're going to reduce this vortice, and the wing is going to be more effective. I think I got a picture here of a Piper Tomahawk, and it's got some pretty good drooped wingtips. Winglets, again, we're talking about the same thing. Here's winglets on a 737. These ones are pretty good. Saves fuel because the wings are more effective. We have less turbulence at the wingtips. We get more lift for the same amount of drag. So we're going to get better fuel economy. Here's Airbuses. They have a different kind of a wingtip, but we're still controlling or reducing the wingtip vortices. Wingtip vortices. We increase effectiveness, lift for the same drag. So we have increased fuel economy. And so we're going to get that effect for tip tanks, wingtip droops, or winglets. I even have a picture there of a winglet. Wing fences. There are not a lot of airplanes with wing fences. Here's on I can't remember the name of the aircraft, just made in Great Britain, but it looks like a 727. It's called the Trident. It's got a big giant wing fence. Obviously, the airflow going across the wing is going to go right exactly where they want it. So it's going to reduce, or let's say it's going to control airflow. Can't spell direction, or can't flow airflow direction on the wing. And I got another one. Here's one. This is interesting. Amazing what you can find on the net. Here is a wing fence on top of an F-18. Looks like it's the older F-18. Doesn't have square intakes. So it's going to somehow have the needed wing airflow across the wing. Needs to be nice and stable. And of course, here is a STOL. STOL stands for short takeoff and landing. And they've messed this airplane up good. They got some kind of funky wingtips going on. They've got wing fences, and of course the wing fences are going to keep the airflow going straight over the ailerons. But it's hard to notice, but in this short takeoff and landing aircraft, you notice that the ailerons are actually going down, drooped ailerons, and it looks like, I can't tell for sure, but it looks like slotted flaps. Wow. And of course this airplane, I'll show you another picture shortly, it also has a canard. This is a really short takeoff and landing aircraft. And of course, oh wait, here's the canard. It's putting a wing out in front. Typically on aircraft with canards, the canard is as a slightly lower angle of attack, so it's going to stall first, and that makes the nose go down, and you recover from the stall automatically. I won't go so far as to say canard aircraft cannot stall, but it makes it much, much, much harder. And of course, if you're flying short takeoffs and landings, you don't want to stall. And so here's a canard on a Cessna 182. And so if they put the canard up there and put it at the right angle of attack, it'll stall first and the nose will drop a little bit so the airplane can't stall. And so that makes it a lot safer if you're flying around at really, really slow airspeeds. Of course, T-tails, they're really tough to notice. Here's that Piper again, that Tomahawk with the T-tail. And here's a big old Fokker. Yeah, just so you know, that's F-O-K-K. Oops. E-R. And you can see slotted flaps, you can see spoilers, you can see reverse thrust, and of course what we're talking about here. Wow, it looks, they even made the flap retraction mechanism and stuff. It's even acting, it looks kind of like a wing fence, which I'm sure helps control flow over the flaps, so the flaps are more effective. Funky flight controls. These are flight controls that have been designed by James Brown, the godfather of soul, or the hardest working man in rock and roll. Stabilators, already covered stabilators. That's effectively the elevator and the horizontal stabilizer in one device, or you could say it's a flying elevator. The whole thing moves. Rudder vaders, you might not have seen these. V-tail bonanzas are the classic example. V-tail bonanzas, you could reduce drag because now you only have two flight controls, two stabilizers out here instead of one. Does the job of both elevators and rudder. And the flight controls inside the cockpit are the same, but there's a box back in here that the cables and push-pull tubes come into and tell the rudder vaders. I guess I spelled that already. Rudder vaders what to do. Cyclic, that's found on a helicopter. Here's what it looks like. It's the stick that you would normally hold with your right hand to control pitch. The cyclic controls pitch and bank. So it effectively tilts that rotor. Oh wait, I think I have a picture here. And here's one in an R-22. That's the one you pull it this way, you bank left, push it that way, banks right, push forward, you reduce pitch, pull aft, and it increases pitch. I think I got a picture. Here we go. So you're essentially that cyclic in here. You can see the little cyclic point. It's right here. Whichever direction you point it, it's going to tilt the rotor disc in the direction you're going. Now, most of the time, let me rephrase that, in a hover, all your lift is straight down. Obviously, now your lift is going off at an angle, so you can have some lift straight down and some lift to the side, so the helicopter is going to go sideways. Same thing for tilt, or for pitch. In a hover, if there's no wind, all your lift is going to be straight down, but now all your lift is going to be partially sideways, so some of here is going to be lift, and you're also going to have some backwards thrust. So a cyclic moves the helicopter left, right, forward, and back, or you could say changes pitch and changes bank. The collective, on the other hand, is completely different. The collective, that's what the left hand goes to. Anybody have a grandparent that looks like this? This guy looks like my grandfather. In any case, the collective is lifted up and down, and you're changing all of the pitch. Here's a collective in a Robinson R-22. So if you're the pilot in a helicopter, sits on the right side usually. So right hand on the cyclic, left hand on the collective, and you lift it up or you push it down, and that's for lift. It literally is connected to all three rotor blades at this, and it increases the pitch of all of them collectively, hence the term collective. I think that's number 3. Cool, man. All right. So, for instance, if you're in a hover, if you're sitting here in a hover in a helicopter, and you pull the collective up, the blades go to a higher pitch, and whatever lift it was, that lift is increased, so the helicopter goes up. So that's a completely different kind of a flight control than in an airplane. You don't have to write this down, but if you increase the pitch, you're going to need some more power. So there's, like on a motorcycle, there's a throttle on the collective that you have to increase it. You have to twist it. Whenever you pull the collective up, you got to twist it to get more throttle. Makes flying helicopter a bit more complicated. Excuse me. Then there's the anti-torque pedal. Essentially, if the rotor blade is going in one direction, then the helicopter is going to have to twist in the other direction. So they tend to put a little propeller, it's called a tail rotor, on small helicopters, and it reduces, it blows air in the opposite direction, so the helicopter will stay pointed straight ahead. And you actually have pedals in the helicopter. Here they are, your feet goes on it. Right foot here, left foot there. I think I got a picture out of an R-22. There we go. Here they are. Here's one pedal right here, and here's another pedal right here. Here's the pedal, and here's the pedal. And if you push down on that one, the aircraft yaws. So the anti-torque pedals are there to yaw the aircraft, or to control yaw by changing the pitch on the tail rotor and counteracting the torque. So cyclic, collective, and tail rotor pedals, anti-torque pedals, are what's available in a helicopter. You know about the connections. Any questions or comments or improvements, you know how to get a hold of me. Thank you very much.